From the derivation of energy equation, I think we are in a position right now to solve for some standard typical cases where we may have convection, may not, or may have only conduction. But before we move into the formal solution of convective heat transfer situations, there's one or two interesting problems that I would like to draw your attention to. So, this part of the class is going to be a tutorial where I would solve a problem and also give you a problem to do it on your own. So, the problem that we are dealing with is a very interesting one. Let us consider two cylinders which are concentric to each other. So, you have one cylinder and another cylinder enclosed in between, and the gap between the two cylinders is very small. Okay? And it's you get this in practical situations wherever you have a bearing where one of the surface is moving with a high speed and the other surface is stationary. So, in order to reduce friction, whenever there is a high speed in between, high relative speed in between two surfaces, one moving and one stationary, in order to reduce friction we use lubricants. Most of these lubricants are oils which have high viscosity and they act in a way so as to reduce or minimize the wear and tear of the moving system. Now, as I have mentioned, the gap between the moving part and the immobile part is generally very small. So, as to have very little play in the moving part. So, it's moving smoothly, continuously, and at the same time without having direct contact with the stationary surface. So, there is a thin film of lubricant in between. Now, when you think of this situation, it is an ideal case for viscous heat generation, because you have a moving part at a high velocity, a stationary part, and a very thin gap in between. So, the velocity changes from the velocity of the moving part to 0 over a distance which is very small. So, if you think of the gradient of velocity, it is v of the moving part minus 0, which is that of the velocity of the stationary part, divided by the distance between the two, which is very small. So, the numerator is large, the denominator is small. So, therefore, this ratio is going to have a large value. And remember that we have seen, and I have told you that the viscous heat generation is generally gradient square multiplied by viscosity. So, a large number V by d, where d is the separation between the two, a large number is squared and multiplied with density, multiplied with viscosity, and the viscosity of the lubricating oil is generally high. So, this is potentially an ideal candidate for viscous heat generation. So, fine, we have viscous heat generation, but what are the implications? Let us say the surface which is moving has some temperature T, T1, Tb, the base temperature, and the surface which is stationary has another temperature. So, when are you choosing a lubricant for this specific purpose, you have to make sure that the temperature of the entire system is not going to exceed the rated temperature for a specific lubricant. Every lubricant has a maximum temperature that it can withstand. If you go beyond that temperature, the ingredients of the lubricating oil, they start disintegrating, dissociating. Therefore, thereby reducing the efficiency of the lubricant. You lose your lubrication property, and that is a disaster when you have a high speed rotating system in contact with a stationary system through a lubricant which is failing, which is not working anymore. So, every lubricant has to be rated for the maximum operating temperature, and then you choose the lubricant based on whatever be the temperature of the inner cylinder, because let us say the inner cylinder is at a higher temperature, the outer is at a lower temperature. But is that correct? Are you correct in assuming that the maximum temperature of the lubricant in between these two parts is going to be equal to the temperature of the surface which has a higher temperature? So, we are going to test, we are going to analyze the situation to find out, are we correct in assuming that the maximum temperature is going to be the temperature of the hot surface, and therefore, if we know the temperature of the hot surface, I can choose a lubricant that can withstand that temperature. But so we would see whether we are correct or not, and if not, what is the remedial measure, how do we calculate and decide which lubricant to choose. So, the system looks something like this, as I have drawn over here. These are cylindrical systems. So, these two are essentially concentric cylinders, okay, one inside the other, and you are going to have the inner cylinder which is stationary. The separation between the two cylinders is B, and the radius of the cylinder is equal to R, and what we are saying is that this B, the separation between the two cylinders, is very small as compared to the radius. So, this is what we have, and the intervening space is filled with the lubricant. So, we have lubricant in here. Okay. So, this is the lubricant. The temperature of the inner cylinder, is T naught, and the temperature of the outer cylinder is T B, okay, and we will assume that T 0 is greater than T B. What we need to find out is what is the temperature distribution that we have in the lubricant. Am I safe to assume that the maximum temperature of the lubricant is going to be T 0, and of course, the minimum is going to be T B, and therefore, my selection of lubricant should be based on T naught. So, this is the system that I would like to model and I would like to analyze. The first thing that one can do, which you probably have studied in your in your fluid mechanics, that if the gap between two systems in cylindrical coordinates is very small, then you can convert the cylindrical system into a Cartesian coordinate system without introducing significant or any appreciable error. So, I have two cylinders like this. Okay. This inner one is rotating, the outer one remains stationary, and the gap is so small in between the two. This system can be analyzed without any loss of accuracy by opening them up and making them as two flat plates. So, the cylindrical system can be converted to a flat plate system where one of the plate is moving, the other one is stationary. We can only do that when the gap is very small compared to the radius, or in other words, the curvature is going to be very small, and for a large R and small gap, this is a perfectly valid assumption of converting a cylindrical coordinate system to a rectangular coordinate system without any loss of accuracy. This helps us in whenever we have a Cartesian coordinate system, we would always prefer a Cartesian coordinate system because the resulting equations are easier to handle. That is the only advantage. You can also do this problem by keeping the system as it is and choosing the equation related to choosing the equation from the cylindrical coordinates form of the equation of energy. But since B is very small compared to R, I can convert this system from cylindrical to a rectilinear coordinate type of systems. So, this looks like the system now then looks like it's two parallel plates, okay, where the separation between the plates as in the problem is equal to B, and let us say this is the one which is the top plate. So, this has the temperature as in the figure, this has a temperature equal to Tb, and it is moving with a velocity which must be equal to r times omega, where omega is the angular velocity. So, the linear velocity here is simply v is equal to r omega, and the temperature over here is T0, temperature over here is Tb. So, we would expect this Tb is more than To. So, we would like to see if we have the maximum over here or that is not the case. Now, since the top plate is moving and the bottom plate is stationary, in your fluid mechanics you have probably read this to be as known as the Kweith flow. Kweith flow is the one in which you do not have any pressure gradient imposed on it. The top plate is moving, and therefore, it is going to drag the liquid below, and this layer of liquid is going to drag the layer below it, and so on. So, the motion of the top plate is being transmitted through the liquid due to the presence of viscosity in it. So, if you can draw this, the layers are going to move like this. As you move away from this, as you move away from the moving plate, the velocity progressively decreases, and due to no slip condition, the velocity is going to be 0 over here. So, the velocity profile for a system like this looks something. So, this velocity, let us say this is my z direction and this is my x direction. So, the velocity is going to be only in the z direction, and it is going to be a function of x alone. So, the motion of the top plate is going to induce velocities at different layers of the lubricant present in between the moving part and the stationary part, and it is going to be linear distribution of velocity, and the non-zero component of velocity, it is going to be a one dimensional flow. So, Vz in the z direction is going to be a function of x, and it is going to be a linear function of x. This type of flow is known as the Kweith flow, which you would see, and starting with the equation of motion, you would be able to obtain this velocity in the z direction to be equal to x by b multiplied by v. So, this is from the Navier-Stokes equation. So, the Navier-Stokes equation in the absence of any pressure, and these are horizontal. So, the effect of gravity is not present. It is simply going to be del square Vz by del x square plus del square Vz by del y square plus del square Vz by del z square multiplied by mu is going to be equal to 0. This is the Navier-Stokes equation. I am sure that you are aware of it, and since Vz is a function of x alone, so this term is 0, this is 0, I cancel mu. So, what you have then is d2 Vz by dx square to be equal to 0, and this is then going to give you as Vz to be equal to C1x plus C2, and the C1x and C2 are the boundary are the integration constants, and the boundary conditions are at x equals 0. That means, on the plate the Vz is 0, which is the no slip condition, and at x equals b, that means on this plate Vz is going to be equal to capital V. So, these are the two boundary conditions with which you would be able to solve for C1 and C2. It is a linear distribution, and this would give rise to the linear form of the variation of the non-zero component of velocity, which is Vz as x by b times V. So, this is kth flow and this is without any imposed pressure. So, if there is an imposed pressure present in the system, then this straight line behavior is no longer going to be valid, and you will have a different type of velocity profile. I think I will not discuss that. You have probably studied that in your fluid mechanics. So, this is the relation which is going to be useful to us when we solve for the energy equation. So, in this entire thing what we have done is we have converted the lubricant bearing system from cylindrical to a Cartesian coordinate, top plate moving, bottom plate stationary, and we identify that the velocity is going to be like this. So, let us see what is going to be the energy equation for this case. The energy and you can also see that the motion is going to be in this direction, and the energy is going to be transported in a different direction. Okay. And this is a case where viscous dissipation is significant. So, if viscous dissipation is significant in here, then the viscous dissipation form of the equation of energy must be used for a rectangular system. So, what is that? I will use this this one once again, and if you look carefully over here, first of all it is a steady state system. So, del T by del temperature time, this is going to be equal to 0. So, this term is going to be 0. This contains Vx del T del x. Once again, if you look at this, this is x and this is z. So, I only have Vz, I do not have a Vx. So, in this case Vx and Vy all are equal to 0. So, if that is the case, then in this equation, this Vx term would be 0, Vy term would be 0, and you have Vz times del T del z. So, what I can write then from the left hand side of the equation is that rho Cp Vz del T del z would remain on the left hand side. And let us see what I have on the right hand, what will remain on the right hand side. The right hand side, I have k del 2 t del x square. K del 2 t del x square, if you look at this, temperature is a function definitely of x, right. This is my x direction. So, the first term would remain in the expression del 2 t del y square, temperature is not a function of y, and del 2 t del z square, temperature is not a function of z as well. So, the only remaining term over here is going to be del 2 t by del x square. Then comes the viscous dissipation terms. So, what are the viscous dissipation terms that you would see? The viscous dissipation is del Vx del x. Velocity is not a function of there is no x component of velocity, there is no y component of velocity, there is a z component of velocity del Vz, but that is not a function of z. So, this is del Vz del z whole square. So, since there is no variation of Vz with z, so this term would also be equal to 0. I have in this del Vx del y plus del Vx del z, all both of these terms are equal to 0. In here I have del Vx del z, which is 0 since Vx is 0. I have del Vz del x. Now, if you look at this figure once again, I have a Vz and this Vz is a function of x. So, del Vz del x term must be present in this term, I cannot neglect. Here I have del Vy del z and del Vx del y, both are equal to 0. So, what I then have on this side from my energy equation is del Vz by del x whole square. So, the entire complicated looking equation, the energy equation in rectangular systems, they resolve, they can be broken down to this. Now, once again I take your I draw your attention to this, where the temperature is a function of x, temperature is not a function of z. This is my z direction. So, temperature is not a function of z, temperature is a function of x. So, if temperature is a function of x, then and not of z, so T is not a function of z. So, therefore, this term can also be set equal to 0. And now, I realize that temperature is a function only of x, Vz is a function only of x. So, therefore, the entire equation then can be written as k d2t dx square is equal to minus of mu dVz by dx whole square. And so, this is the governing equation for the system that we are analyzing. What is dVz dx? My Vz is this. So, my dVz dx is simply V by B. So, therefore, since Vz is equal to x by B times V, this would give me dVz by dx to be equal to x by V by B. So, therefore, my equation becomes further simplified, minus mu times V by B whole square, or I can drop the k from this side and bring it over here. So, you integrate it, this is a simple ODE, you integrate it twice and you are going to get minus mu by k V by B whole square times x square by 2 minus C1 by k x plus C2. These two C1 and C2 are the constants of integration. In order to evaluate this, you need two boundary conditions. So, what are the boundary conditions? You can see that the temperature at z equals 0, temperature at x equals 0 is T0, temperature at x equals b is Tb. So, the boundary conditions are x equals 0, T is equal to T0, and at x equals b, T is equals Tb. Use these two boundary conditions to evaluate C1 and C2. And what you should get, and I think you should do it on your own to check that you are getting the correct form, what you would get is this form of the temperature distribution, T minus T naught by Tb minus T naught is equal to x by b plus half of Br, and I will tell what Br is, x by b times 1 minus x by b. Please do it on your own and see that you are getting this form. It is extremely important to practice these so that you do not make any silly mistakes. So, you have a straightforward equation, to integration constants, to boundary conditions. So, evaluate C1 and C2 in order to get the form of the expression which I have written over here. Now, this Br is very interesting. This Br is known as Brinkmann number. And you would see when you do it on your own, this Brinkmann number is nothing but V square by k into Tb minus T naught. Once you solve it, you are going to get this as your number. So, Brinkman number essentially tells you the extent to which viscous heating is important relative to the heat flow from the imposed temperature difference. Which in this case is simply equals to Tb minus T naught. So, it is clear that mu v square by k into Tb minus T naught, you can divide this side by L square and the denominator by L square, and from the definition of viscous heat you can see that the top refers to the viscous heat which is generated, whereas the bottom is the imposed temperature difference. So, they refer to the conductive flow of heat. Now, let us see if we get back to something which we would expect. Let us say that in this there is no viscous heat generation, there is absolutely no viscous heat generation, only conductive heat flows from the high temperature to the low temperature. So, this is a case in which two end temperatures are known, it is steady state and there is no heat generation. So, for a case where you have steady state, no temperature difference and the two end temperatures are known, the temperature distribution will be linear. That is what we have seen so many times, that two end temperatures are known, no heat generates in between. So, there is going to be a linear distribution of temperature. So, how do I see if our analysis is correct? As I mentioned to you previously, always look at the limiting form of the solution. Look at the limiting form and see if it reverts to a form which is known to be correct to you. So, how do I make sure that there is no viscous heat generation? Let us say that there is no velocity. So, if there is no velocity, then this second term on the right hand side, what you see over here by the Brinkman number, let us put this to be equal to 0, V to be equal to 0. So, the entire second term will be 0 and what you get is a linear distribution of temperature in the medium. So, this part is for linear distribution which is caused by conduction only, and the second one is due to viscous generation of heat. So, this Brinkman number therefore refers to viscous generation of heat in a system where the thickness is very small. But even this is not interesting, there is something more interesting to it. What you can do it, you can do it on your own to see that if Brinkman number is greater than 2, there is a maximum temperature at a position intermediate between the two walls, between the two walls. This is probably the most important part of the exercise. You have a temperature distribution, find out what is the maximum temperature that you can get. So, you find out what is dT dx, set it equal to 0 and see that for when you find out dT dx and set it equal to 0 from this expression, you would see that Brinkman number, if it is greater than 2, then you are going to get a maximum temperature at a position in between these two. So, if you do not have any flow, if you do not have any viscous dissipation, the maximum temperature is going to be at Tb. But if your Brinkman number is greater than, so the profile in that case would look like this, a linear distribution. But if you get a Brinkman number greater than 2, then the profile may look like this, and therefore the maximum temperature would lie at a point in between the top plate and the bottom plate. This is the interesting result. Why is this the interesting result? Because you have chosen your lubricant based on Tb, the maximum temperature that you think is present in the system, which is the temperature of one of the plates. But due to viscous heat generation, there is a point where the temperature exceeds that of Tb. So, your choice of lubricant should be dictated by this temperature and not by this temperature. So, the intermediate position temperature, if it exceeds the temperature of the upper plate, then it would be wrong for you to choose the lubricant based on Tb. Rather, you have to see what that temperature would be from this expression and find out and specify the lubricant. So, in any lubrication system where there is viscous heat generation, you must find out what is the value of the Brinkman number. If the Brinkman number is greater than 2, you must do further calculation to find out where is the maximum and what is the value of the maximum temperature for such a system. So, a simple analysis, a simple problem can give you so many ideas, new ideas about how to treat conduction, how to use, first of all, how to use the equation of energy, how to cancel the terms which are not relevant, see the importance of conduction, when there is flow present, but in a direction perpendicular to the heat flow. Therefore, you are not considering convection explicitly. However, the presence of the velocity in your equation, or rather the presence of the velocity gradient in your energy equation, tells you that you need to probe further in order to obtain how would the shape of the temperature profile look like. More importantly, are you going to get a maximum in the profile due to generation of viscous heat in between the top plate and the bottom plate? And the number, the dimensionless number, which tells you the importance of viscous heating relative to the temperature, imposed temperature gradient, relative to the heat flow due to the imposed temperature gradient, which is known as Brinkman number, that plays a critical role, and you must find out what is the value of Brinkman number before you choose a lubricant. So, from concepts to practical applications, this is one example which I think would be interesting to anyone who is studying convective heat transfer.